Yes, good morning, everyone. Welcome to the online education section or session arranged by the Education Department of Municipal Corporation of Greater Mumbai. Right. So today, the subject we are studying is science for class 9, and the topic that we are going to be studying today is study of sound. Okay. So this is the first session, and within that, we are going to be studying about sound waves. My name is Vishal Choudhary, and I am from the Kurar Village MPS English Secondary School. Okay, so let us move into the chapter and try to learn the concept of sound. Okay, so the topics that we are going to be studying within this chapter are, the first one is your sound waves, right? So here we are going to study exactly what is sound, how is sound generated, how is sound moving around, right? Sound, how it propagates, the waves that are formed by the sound. Okay, so the types of waves also we are going to be studying, the characteristics and properties of the waves we are going to study in this section, right? There we are going to talk about longitudinal waves and transverse waves, right? And also about their properties. After that, we are going to study about the velocity of sound, right? We are going to see the definition of velocity of sound. Then we are going to see the mathematical formula for the velocity of sound. Then therein we are going to study how the velocity of sound varies, mean how it differs in different mediums, right? So within the definition of sound waves, we are going to see how sound requires a medium to travel in. Okay, so within the section of velocity of sound, there we are going to see how the velocity of sound is different in different mediums, as in solid, liquids, and gases, right? Also, we are going to see how the various factors affect the velocity of sound. Okay, then the next concept will be about the reflection of sound, right? How the sound reflects from various surfaces. There we are going to see a very interesting concept of the echo, formation of echoes, right? Then after that, we are going to study the concept of the human ear, the various parts of the human ear, right? How we perceive the sensation of hearing through the different parts within our human ear, right? Then we are going to study the various forms of sound, that is the audible sound, the sound that we can hear, right? Then the other forms of sound, that is your infrasonic sound and the ultrasound. And also the various applications where infrasonic sound and ultrasonic sound are used. Okay, so let us now move into the concept and start studying about the sound. Okay, so first of all, we'll see the definition of the sound. Okay, so sound is a form of energy which creates a sensation of hearing in our ears, which is perceived by our brain. Okay, so sound is a form of energy which is produced through vibrations. Okay, so for production of sound, you need a source of sound. Source of sound, you can imagine like a loudspeaker. Okay, so when a loudspeaker is working, what happens is the face of the loudspeaker starts vibrating. Okay, vibrating means it oscillates, it moves back and forth. So as it moves back and forth, that is when it vibrates, it sets in motion the air particles which are in contact, right? And it sets and forms waves, right, which move through the air, travel through the air, and then they reach our ear. So inside our ears, right, the ears convert those vibrations into signals which our brain perceives as the sensation of hearing. Okay, so in the further parts of this chapter, we are going to see how those waves are formed, how they move about, and how we perceive the sensation of hearing in our ears. Okay, so the definition of sound is what? Sound is a form of energy which creates a sensation of hearing in our ears. Okay, then we are going to see now the properties of sound waves. Okay, so as I've told you, sound energy travels in the form of waves. Okay, so these waves are generated by the source of the sound, which can be a loudspeaker, or maybe when you are speaking, they are the vocal cords within our throats, or your neck within your throat. Okay, then a medium is necessary for the propagation of sound waves. Now if you observe the diagram, the animation below, you can see there is a loudspeaker or a speaker, right? Now when that speaker works, the face of the speaker starts vibrating, right? Now when it vibrates, it starts, or it's set into motion, or it starts the air molecules into vibration. Now, when these air molecules start vibrating, they transfer their vibrational energy to the neighboring molecules, and this vibrational energy propagates throughout. So if you can see from the loudspeaker, the wave, the vibrations are moving from left hand side towards the right hand side. So one most important property of the sound wave is that it requires a medium for it to move in. Okay, so sound waves cannot travel through vacuum, right? So in deep space, sound waves cannot travel. So for sound waves to move, it needs a medium. So that means the medium can be either a solid or a liquid or a gas. That means sound waves can travel through all the three mediums of solid, liquid, and gas. Okay, so further we are going to see how sound travels in all of these three mediums and how differently the velocity of sound changes. Okay, now let us move on further. Okay, so sound waves gives rise to a chain of compressions and rarefactions in the medium. Okay, now what are these compressions and rarefactions that we will talk about? Okay, so now if you look at this animation or the diagrammatic representation here, right, now you can see that the wave is moving from left hand side to the right hand side. Okay, so now these black dots, they represent the air molecules or the molecules or particles of the medium. Now here you can imagine that these particles of the medium are of a gas. Okay, so these black particles and some of them are red so that you can see how exactly they are vibrating. Okay, so from the left hand side you can see, you can imagine on the left hand side there can be a loudspeaker. Now when that loudspeaker, the face of the loudspeaker vibrates, it sets into motion or it sets into vibration the particles which are immediately in contact with the loudspeaker, right? Now if you can imagine the red colored particle, you can see how it is moving back and forth from left to right, but it is not moving as a whole, right? It is maintaining its mean position. Okay, but you can see that the wave, it moves from left to right. Okay, so now you can see there are certain dark bands which are moving from left to right. Okay, now these dark bands, they are regions of compression. You can see the particles come close over there, and there are certain regions where the particles move further apart from each other, and these regions are the rarefactions. Okay, so the compressions are the regions where the particles are very close to each other, right? Here, the density as well as pressure of the particles or pressure of the gas is more or it is increased. Whereas in the rarefaction, it is a region where the particles are further apart from each other, the pressure decreases, right? And density also decreases. So you can see that the compression means the high pressure regions and the low pressure regions, they are alternate. So you can see there is a compression, after that there is a rarefaction, then after that again there is a compression and rarefaction. It repeats. So there are alternate compression regions and rarefaction regions. So these waves, the sound waves, travels further in the form of these compressions and rarefactions. Now you can imagine this wave as a graph below. Now you can see that blue line which represents the graph. Now the compressions and rarefactions here are shown in the form of a graph, right? Now the top region, right, where the wave has a peak, right, it is a compression, it is represented by that peak, whereas the rarefaction is represented by the dip in the curve below. So the peak on this wave, the blue wave, the peak is called as a crest, whereas the lower region is called as a trough. Okay, so you can see those compressions and rarefaction, they are moving in the form of the wave. Okay, so here we are now going to study the different types of waves which are present. Okay, so let us now move into the next concept, that is the types of the waves. Okay, that there are two types of waves which are longitudinal waves and your transverse waves, right? Now let us first of all study about the longitudinal wave. Okay, so the definition goes as, in a longitudinal wave, the particles of a medium oscillate about their mean positions in a direction parallel to the propagation of the wave. Okay, so if you can see here, the red particle, it is moving from left to right, but it maintains its mean position. Its average position remains constant. But you can see the wave is moving from left hand side of the screen to the right hand side. Now you can see the regions of compressions and rarefactions, they are moving also from left to right, and also they are alternating. So you have alternate regions of compressions and rarefactions which are moving from left to right. Okay, now the important thing that you need to observe here is the wave is moving from left hand side to the right hand side, whereas all the individual particles, they are also vibrating from left to right. So if you can see, the direction of vibration of the particle and that of the wave, they are parallel to each other. So in a longitudinal wave, the direction of oscillation means vibration and the direction of the wave motion are parallel to each other. So in a longitudinal wave, you need to remember that the direction of vibration and the wave motion are parallel to each other. And sound waves travel in the form of these longitudinal waves, right? Now let us next see the next type of wave, which is a transverse wave. Now let us first go into the definition, then I'll give you an example. Okay. So in a transverse wave, the particles of the medium oscillate about their mean positions in a direction perpendicular to the propagation of a wave. Now for this, the example that you can imagine is a stone which is dropping in water. Now, when a stone is dropped in water, what happens is the stone sets into vibration in the particles of the water, right? And if you observe it from above, you can see the wave moving around in a circular concentric pattern, right? But if you observe this, you can imagine that that red block to be the stone dropping in the water, right? And the line which is represented here can be the surface of the water, right? So you can see the red particle can be an individual water molecule and you can see it is moving up and down, right? Whereas the wave, as you can see, it is going from left to right. So in this case, the direction of vibration is up and down, right? Whereas the wave is going from left to right. Okay, so you can see the vibrational direction or the oscillation is up and down, and the wave is moving from left to right. So you can see that the direction of oscillation and direction of wave motion is perpendicular to each other. All right. So this is a transverse wave, right? So you can see the crest at the top and the trough at the bottom of the wave. Okay. So you can see also here the distance between the two crests is shown here, which is called as a wavelength. So distance between the two top ends or the two top crests of a wave, right, is a wavelength. So we are going to see exactly what wavelength is, and also we are going to see about the different properties, right? So you can see we have seen here the transverse wave, and before we have seen the longitudinal wave, right? So sound waves travel in the form of longitudinal waves, whereas other waves, as in your light energy or maybe electrical energy, they are in the form of these transverse waves, right? So we will be studying those in further different chapters. Okay, now let us move on ahead. Okay, so a sound wave can be shown in the form of a graph that we will study here in this figure on the right hand side in the form of figure A, B, and C. Okay, so at any moment during the propagation of sound wave, we can find alternate bands of compression and rarefaction of the medium, that is the bands of high and low density. Now let us imagine, let us observe this figure in detail. Okay, so you can see here in the figure on the left hand side, you can see that there is a loudspeaker which is vibrating. So when it vibrates, as we have seen previously, it sets into motion the air molecules which are in contact with the surface of the speaker, right? So it generates those alternate regions of compressions and rarefactions. So those arrows at the top of figure A, you can see those arrows are going from left hand side to the right hand side. Okay, so you can see those alternate bands of compressions and rarefaction, right? Now the changes in pressure can be shown in the figure B. Now you can see those bands of compression. The dark bands are situated very close to each other, which represents a high pressure region. Whereas in the rarefaction, those bands move further apart from each other, which are the low pressure regions. Okay, so if you want to show them in a graphical manner in figure C, you can see that the density or pressure is shown on the vertical axis. So it goes up and down, whereas the time or the distance traveled by the wave can be shown on the horizontal axis, right? So you can see the wave is moving from left to right. Now the regions of compression, the wave, it goes upwards because of high density and pressure, whereas in the rarefactions, the wave goes at a bottom part of the wave, which is your uh, trough of the wave, right? Now you can see here the symbol lambda is shown here, which is your wavelength. Now the wavelength can be the distance between the alternate crests or alternate compressions or alternate rarefaction. We will see further definition of your wavelength. Okay, so that is about your properties of a wave. Now let us move on further. Okay, so we are now going to study the characteristics and the different properties of a sound wave. Okay, the most important properties of any wave is its wavelength. Okay, so the distance between two consecutive compressions or rarefactions is called as a wavelength, and it is indicated by the Greek letter lambda. Okay, now if you observe this wave, right, now your sound wave, the longitudinal wave, acoustic sound wave, acoustics means energies related to sound. Okay, so you can see those compressions which are shown as dark bands and rarefactions as your light bands. So these compressions are shown at the bottom wave in the form of a crest, right? The top peak of the wave. Okay, so the distance between those two consecutive peaks, which we call as crests, is called as a wavelength. Okay, and all waves have a characteristic wavelength, right? So every wave should have a given wavelength. It is a very important characteristic property of a wave. Okay, so it is given by a Greek letter lambda, and its unit is in the unit of your length. It can be either meter or centimeter, right, or any other smaller unit also, be nanometers and so on, right? So the unit of your wavelength will be your unit of distance, that is meters or centimeters or whatever. Okay, now let us look at the next property of a wave, which is your frequency. Okay, now the frequency is the number of oscillations per unit time of a wave. So the number of oscillations per unit time is a frequency of a wave, and it is indicated by nu, a Greek letter which is nu. You can see there in the bracket, right? Now, frequency relates to how many times a given particle is vibrating. Okay, now you can see here that the wave has the same velocity. Now, if you look at these two different examples on the left and the right, you can see that the wave is moving with the same speed. The wave velocity is constant, but you can see on the left hand side, the vibrations are less. You can see on the left hand side, a red particle is going up and down slower, but on the right hand side, you can see the red particle is going up and down faster, right? So the wave on the right hand side is of a high frequency, and the wave on the left hand side is of a low frequency. Now, low frequency always corresponds with a wave of a longer wavelength. Okay, and the wave of a higher frequency will correspond to that of a wave with a lower wavelength. Okay, one more important concept is that waves of lower frequency are higher energy, they have more energy, and waves having a lower frequency will have a lower energy, right? So that is an important concept. Okay, so wave frequency is what? The number of times a given particle oscillates in a second, right? So frequency is nothing but number of vibrations per unit time. Its unit is called as a hertz, Hertz, hertz. Okay, okay, and 1 hertz is what? 1 oscillation per second. So if a particle oscillates once in 1 second, then that is called as 1 hertz frequency. Okay, so far we have seen what the concept of wavelength and the next concept of your frequency. Okay, now let us move on further and study the next concept, that is called as an amplitude. So the amplitude is the maximum value of pressure or density, and is indicated by letter capital A. Now, the amplitude relates to how loud or soft a sound is. Okay, so if you can see the left, on the left hand side, the top wave, right? On the top side wave, you can see the amplitude is smaller, whereas in the bottom wave, the amplitude is larger. So the top wave, it is a soft sound, and the bottom wave is a louder sound. So if you want to imagine, if I'm talking in a very soft manner, that can be the top wave. But in the same way, if I talk louder, right, that will be the bottom wave. Okay, if you see here, the wavelength of the waves as well as the frequency is the same, but the amplitude changes the loudness of the sound. Okay, so amplitude relates to how loud or soft a sound is. Okay, let us move further, right? The next concept is called as a time period. Okay, so the time taken for one oscillation of pressure or density at a point in the medium is called as a time period, and it is indicated by the letter capital T. Okay, so time period is nothing but the time taken for one complete wave to pass a given point in the medium. Okay, so one wave will be what? One wave will correspond to two similar points on the wave. So those two similar points can be either two crests, that is the two peaks, or the two bottom regions of the, that is the troughs of the wave. Okay, so the time period will be the time required for that one complete wave to pass through any given point on the medium. Okay, So far, the properties of the wave that we have seen are what? The wavelength, frequency, amplitude, and time period. Okay, let us move ahead. We will definitely revise all of these again, but let us move on to the next one that is called as a pitch. Pitch of the sound. The pitch of the sound relates to the frequency of the sound. Okay, so let us see a definition. The value of frequency determines the pitch of the sound. So low pitch sound is of a low frequency and high pitch sound is of high frequency. So if you can see in the diagram below, you have a example of a wave having low pitch, means of a longer wavelength, right, and a lower frequency. Whereas the high pitch wave has a shorter wavelength, right, and a higher frequency. So if you can imagine two singers, right, okay, say someone like a male singer and a female singer. So if you can take an example of someone like a male singer like Kishore Kumar or a female singer like Lata Mangeshkar. Okay, now female sounds are very shrill, right? Whereas male sounds, they are heavy, which have more bass. Okay, so male sounds are of low pitch, right? And female sounds are high pitch sounds, high frequency. So you can imagine that Lata Mangeshkar has a sound of a high pitch, whereas someone like Kishore Kumar would have a low pitch sound. So males, right? Males have a deep voice. So that relates to a low pitch, low frequency sound. Whereas high pitch sound will be related to your female voices. Okay, shrill sounds. Okay, so pitch will relate to, right, how a sound is of either a low frequency or of a high frequency. Okay, then next one is the concept of a velocity of a sound. Now, the distance covered by a point on the wave in unit time is a velocity of the sound wave. So we are quite aware about the formula for your velocity. So velocity is given as what? Distance upon time. Okay, now any point on the sound wave covers a distance equal to lambda, which is the wavelength, in the time t, which is the time period. So we have seen the concept of time period, right? What is the time period? Time required for one complete wave to pass through. Okay, so we can write down the velocity of a sound as v, the velocity of sound, equals to nu into lambda, where nu is what? Your frequency. Okay, and lambda is what? Your wavelength. So frequency is what? Number of waves per unit time, right? The number of oscillations per unit time. Okay, now as we know that frequency is 1 by t, okay, we can substitute that value here. So velocity will be equal to wavelength upon time period. Now you can see here we have substituted the value of nu, which is frequency, by 1 upon t. So it becomes what? Lambda upon 1 upon t. Okay, so on solving it, it becomes what? V, the velocity of sound, equals to what? Lambda upon t, where what is lambda? The wavelength, and the t is the time period of the wave. Okay, so this will help us in calculating the velocity of sound in different mediums, right? So let us go through it again. So distance covered by a point on the wave in unit time is a velocity of the sound wave, right? Okay, and its formula, there are various formulas. So for the first one is what? V equals to nu into lambda, where nu is the frequency of the wave and lambda is a wavelength. Okay, now frequency is given as 1 by t. Okay, and where t is what? The time period. What was time period? The time required for one complete wave to pass through a given point. Okay, so if you substitute it there, we will get what? V equals to lambda by t. Okay, where v is what? Velocity of the sound. Lambda is a wavelength of that sound wave, and t is the time period of that given sound wave. Okay, let us move on ahead. Okay, so we can see what? Velocity of sound equals to what? Wavelength into frequency. Now let us see a certain concepts. Now in any medium at fixed physical conditions, the velocity of sound of different frequencies is very nearly the same. So if you have fixed physical conditions of temperature, pressure, right, then your humidity, right, the velocity of sound for different frequencies will nearly remain the same. That means what? As I've told you, different frequencies means your high pitch sounds and low pitch sounds, they will travel almost with the same velocity. So if you have a girl talking and a boy talking, so a girl will have a high pitch sound, whereas a boy will have a low pitch sound. So when they are talking, right, both the sound waves generated by them will reach my ears at the same point, at the same time, right? Because they travel almost with the same velocity. Okay. Then the next important concept is the velocity of sound is highest in solids and least in gases. Yes, sound travels faster in solids, right? Then a bit slower in liquids and slowest in gases. Now, if you can see the diagram here, it is just a simple representation of how a sound will travel, right? So you can see the wave going faster in a solid. You can see that, see the particles, the wave goes faster in the solid, a bit slower in liquids, the blue one, and the slowest, the red one in the gas, right? So that's exactly the way it is present. Okay, so it increases with an increase in temperature of the medium. Yes, so if the temperature of the medium, whatever that medium may be, solid, liquid, or gas, higher the temperature, faster will be the sound wave, right? So if you have an ambient temperature, means outside air temperature, say if it is 40 degrees Celsius, right? Okay, and say maybe the inside room temperature is maybe at 20 degrees Celsius inside an AC, right? The sound will travel faster, right, in higher temperature. Okay, so it is an important concept, right? Then let us go on further and understand how the velocity of sound varies in different mediums. Now, there are certain examples given of solids, liquids, and gases here, right? So you can see the substance aluminum, right? In aluminum, the speed of sound is 5,420 meters per second, whereas in something like nickel, it is 6,040 meters per second. So again, in solids, you can see different solid materials have different velocities of sound within them. Okay, so depending upon the type of the matter, why? Because even solids will have different densities, right? So depending upon the densities, the value of the velocity of sound will change. Same way in liquids, you can see in seawater, the velocity of sound is 1,531 meters per second, whereas in something like methanol, which is an alcohol, it is 1,103 meters per second, right? Same way, like in different gases, you can see in hydrogen, it is 1,284 meters per second, whereas in pure oxygen, it is 316 meters per second. Whereas in our air, which is a mixture of different gases, in air, it is 346 meters per second. You need to remember that with different temperatures of the gases as well as the liquid and solids, the velocity of the sound will change. Also with the changes in density, right? The velocities will change. So these are certain examples, right, that you need to just go through once. Okay, now let us move on further, right? Now, velocity of the sound changes with changes in the physical conditions, right? So the most important is the variation of temperature. Okay, so let us go through it. The velocity of sound is directly proportional to the square root of the temperature of the medium. Right? So you can see the formula, velocity is directly proportional to square root of the temperature. This means that increasing the temperature 4 times will double the velocity of the sound. Okay, so say for example, if you have temperature for gas, say at 20 degrees Celsius, right? Say the temperature of a gas is 20 degrees Celsius and the velocity of that sound in that gas is say x. Let us assume that velocity of that sound of the sound in that gas at 20 degrees Celsius is x. Okay, okay. If you increase the temperature by 4 times, right? So 4 times of 20 degrees Celsius will be how many? It will be 80 degrees Celsius, right? So at 80 degrees Celsius, the velocity will be doubled. That means it will be 2x. Okay, so increasing the temperature by 4 times will double the velocity. Okay, that is what is the meaning here. Okay, so you need to understand the concept here that increasing the temperature of that medium, whatever that medium may be, it can be a solid or a liquid or a gas, increasing the temperature by 4 times will double the velocity of the sound. That means velocity of the sound is directly proportional to square root of the temperature of the medium. In general, in simple terms, velocity of a sound increases with increases in temperature. Okay, let us see the next concept. Variation with density. What is density? Density is mass per unit volume of the substance. Okay, so what is the variation of velocity with density? Let us see. The velocity of sound is inversely proportional to the square root of the density of the medium. So you can see velocity is inversely proportional to square root of the density, right? Now it is similar but in the opposite way as that of temperature. Let us see. This means that increasing the density 4 times reduces the velocity to half its value. So if we increase the density of a gas by 4 times, will reduce the velocity to half its value. Okay, so that is a relation with density. Okay, so increases in density will decrease the velocity of the sound. Okay, the next is what? Variation with molecular weight, right? So what is molecular weight? The sum of the atomic masses of individual atoms in a molecule is a molecular weight, right? So what is the variation with molecular weight? We'll see. The velocity of sound is inversely proportional to the square root of the molecular weight of the gas. That means velocity is inversely proportional to the square root. It is also similar to that of density. This means that increasing the molecular weight 4 times will reduce the velocity to half its value. It is also similar to that of density. Okay, then, right? So there are certain questions that I will want students to be preparing today as a homework. That is, you know, define sound, then define longitudinal waves, then define your transverse waves, then define amplitude and velocity of the sound. Then the next question will be state the factors that affect the velocity of a sound in a gaseous medium. So what are the factors that affect the velocity of a sound in a gaseous medium? That can be temperature of the gas, then density of the gas, then the molecular weight of the gas, right? Okay, so before we conclude today's class, let us once again revise the concept that we have seen today and go through it once again. Okay, so first of all, we had seen, right, the definition of a sound, right? So what is sound? Sound is a form of energy which creates a sensation of hearing in our ears. Okay, so sound travels in the form of waves and it requires a medium. So sound waves are also called as material waves. Why? Because they require a certain material to travel in. Material as in like a gas or a liquid or a solid. Okay, so sound is a form of energy which creates a sensation of hearing in our ears. Okay, then next one. Properties of sound waves we have seen, right? As I've told you, sound travels in the form of waves, right? And a medium is necessary for the propagation of the sound waves, right? And as you can see, when the face of a speaker vibrates back and forth, right, it causes the air molecules in contact with it to also vibrate along with it, right? So the vibrations of the air molecules are transferred from one to the other and the wave is set in motion, right? So the regions of high pressure and low pressure alternatively start moving away from the speaker, right? So a source of a sound will produce those vibrations. Those vibrations will travel through the air and then they will reach our ears where they will generate the sensation of hearing, which is perceived by our brain. Okay, so you can see the sound waves will give rise to this chain or series of compressions and rarefactions in the medium. So as I've told you, compressions are the regions of high pressure and high density, whereas rarefactions are the regions of low pressure and low density within the medium, right? So you can see they move away from the source of the sound. That is the sound, the source of the vibration. Okay, so these vibrations you can imagine to be happening when a sound is generated. So if you want to generate such a thing, you can say have a desk or wherever you are sitting, you can have a table. And on that table, if you strike your hand, if you bang on that table, you can feel that table to be vibrating, right? And that generates a sound. Simpler example is that if you are talking, when you're talking, you can gently place your hand on your neck and you can feel your neck vibrating, right? And those vibrational energies, the sound within your throat, right, through our air pipe, you have, right, it vibrates, and that vibrational energy, the vibrations, they come out from your mouth and travel in all directions. Okay, then next is what the types of waves that we have seen. Here is the concept of your longitudinal waves, right? So in a longitudinal wave, the particles of the medium oscillate about their mean positions in a direction parallel to the propagation of the wave. So you can see here the particles are oscillating left to right and back and forth, right? Whereas the wave is moving in the direction from left towards the right. So you can see the direction of wave particle vibration, I mean the direction of the particle vibration and the direction of wave motion, they are parallel to each other, right? So your sound waves travel in the form of these longitudinal waves, right? So other example is that of a transverse wave. In a transverse wave, the particles are vibrating in a direction which is perpendicular to direction of the wave motion, right? So you can see the particles are moving up and down, right? Whereas the wave is traveling from left to right. So that direction is perpendicular. Okay. Then the next we had seen was the concept of sound waves. You can see how the sound waves are formed by the changes in density, and it moves from left to right, right? So at any moment during the propagation of a sound wave, we can see those alternate bands of compressions and rarefactions, right? So where the bands of high and low densities are formed, which are your compressions and rarefactions. Okay. Then we had seen characteristics of sound waves. The first of them was your wavelength, right? So wavelength is what? The distance between the alternate crests and troughs, right? So the distance between two consecutive compressions or rarefactions is called as a wavelength, and it is given by the symbol lambda. Wavelength is the most important characteristic property of a sound wave or any wave. Okay. So two different sounds, right? So when you are hearing, you can distinctly hear two different sounds. So you can imagine a person speaking from outside the door with the door closed, but you can identify the person who is talking. It is based on the wavelength. So me talking right now, right? My sound generated by me will have a distinct wavelength, whereas a sound generated by a certain other person will have a distinct other wavelength, right? Which we can listen to and hear and identify. Okay, so wavelength is what? The distance between two consecutive crests or two consecutive troughs on a wave, and given by the symbol lambda. Then next is what? Your frequency. So frequency is what? The number of oscillations per unit time. Okay, the symbol is your nu and the unit is hertz. Okay, so a high frequency wave, in a high frequency wave, the particles will vibrate faster. You can see on the right hand side example. Whereas in a low frequency wave, the particles will vibrate slower, but the velocity of the wave will be the same. Only the speed with which the particles vibrate will be different. Okay, so you can see the wave velocity in both the cases, the wave is moving with the same velocity, but the speed of the vibrations is different, right? So frequency will be what? Right, the number of oscillations per unit time. Okay, then the next is what? Amplitude. So the amplitude is a net displacement, right? Means how, by how much extent is the particle getting displaced. So the amplitude is the maximum value of pressure or density. So when you can imagine a vibration when a particle is going from left to right, okay, so if you can measure the extent by which it is vibrating, it will be the amplitude, right? So bigger vibrations will be having more amplitude, whereas smaller vibrations will have a lesser amplitude, right? So bigger vibrations will generate louder sound, right, and a higher amplitude, whereas smaller vibrations will be having a lower amplitude and a softer sound. Okay, so amplitude is given by a letter A, and the unit for amplitude is also the unit of the length, that is meter or centimeter or whatever other smaller unit of length that you can have. Okay, then the next is what? The time period. So time period is a time required for one complete wave to pass a given point, right? So the time taken for one oscillation of pressure or density at a point in the medium is called as a time period. It is given by the letter T. Okay, so time period is nothing but the time required for one complete wave to pass through. Okay, then the next is what? A pitch. Now pitch of the sound relates to high frequency or low frequency of the sound. So high pitch sound will be of a higher frequency and low pitch sound will be of a lower frequency. So I had given example, right, of singers, right? So a male singer singing will have a low pitch sound, whereas a female singer singing will have a high pitch sound. Okay, then next we saw the concept of your velocity of a sound. So the distance covered by a point on the wave in a unit time is the velocity of the sound wave, and velocity is given as distance per unit time. Any point on the sound waves cover a distance equal to lambda in the time period t. Okay, so velocity is given by v equals to nu into lambda, that is what your frequency into wavelength. Frequency can also be written as 1 upon t, right? So you can also write velocity of sound wave to be wavelength upon time period. Okay, then you can see here velocity of a sound differs in different mediums. As I told you, sound travels faster in solids, then a bit slower in liquids, and slowest in gases. Okay, and velocity of a sound will depend on the physical conditions prevalent at the time. Okay, so let us see, right, as we have seen here, the various examples of solid, liquid, and gases, and the different speeds at which the sound travels within them. Okay, so you can see here solids have the highest speeds, then you have liquids, and then you have gases. Also, important thing to notice here is that two different solids will have two different speeds with which the sound will travel within them, right? Yeah. Next is what your variation and velocity of the sound, right? So temperature, what temperature, as temperature changes, the velocity of sound changes, right? So the sound, the velocity of sound is directly proportional to the square root of the temperature of the medium, right? This means increasing the temperature 4 times will double the velocity. Then next was your density, right? So the velocity of sound is inversely proportional to the square root of the density. That means if you increase the density of the medium, the velocity of the sound will decrease. Okay, so if you increase the density by 4 times, the velocity will become half of its initial value. Okay, the next is what? Variation in molecular weight, right? What was molecular weight? Sum of the atomic weights of all the atoms in a given molecule. Okay, so if you want to have something like oxygen molecule, right? So the atomic mass of oxygen is 16 units. Oxygen molecule will be O2, so there are two atoms, so molecular mass of oxygen will be 32 units. Okay, so that is what is molecular weight. Fine. So the velocity of sound is inversely proportional to the square root of the molecular weight of the gas. This means that increasing the molecular weight 4 times reduces the velocity to half its value. So you need to remember this. Okay. Okay, and then I had, as you had seen previously, I had given these questions for certain definitions, and I give one question more that you need to be solving, right? So then we will move and meet into the next lecture. Okay, Almas madam.
Yes, sir.
Yes, madam, you can conclude the class.
Actually, sir, 8 minutes are there. So if you can revise or
Yes, I have
elaborate.
already. Okay, if any students want to ask any question, you can ask, please. You can raise your hand and ask any question.
Yes, students, if you are having a doubt or any question, you can raise your hand. I will unmute you and you are able to ask the questions. Okay.
Students are expected to write down as homework the questions that I have given. Okay, so in the next class, students who have done the homework will be answering my questions regarding the homework. Okay.
Okay, sir. Thank you.
Yes, madam.
Okay.
Okay, madam. Thank you.